Um, part one was on Friday. So you remember that I gave you that list of all the different types of problems, and many of them are sort of what I call grade 11 problems. The three sort of grade 12 ones are on Monday we did car driving off a cliff. Today we're going to do catcher throwing the baseball sort of like projected horizontal ground, and then tomorrow we're going to project things off cliffs, kind of thing. Sort of the big daddy, the culmination of all of them. And it looks like I need to go ahead and do this again. And let's begin. So here's a little animation that I've got that kind of explains this a little bit. This is more, you like that? This is more what we did Friday, right? This would be projected off a cliff, right? And the faster the speed, can I do that? No, that goes up and down. Oh, I can't do the speed here? No, I can't. But if I lower the gun, it's not going to go as far, right? How come it doesn't go as far? Because it takes less, oh, I thought class had started. Because it takes less time for it to actually fall, right? So it isn't able to go as far horizontally, kind of thing. So just something neat that I found. I should actually put it probably on the, yeah, put it right at the top. Well, that's as high as it goes. Could you predict where it's going to land? You should be able to. As long as you know the height, it says the initial velocity is 31.3. Where they came up with that, I don't know. This is actually 98.1 to the height. The initial vertical is 0. Yeah. Anyways, Kurt, I need you to listen. We're ready to go here. Okay, so consider a projectile like a bullet launched to some angle. Whether you write this down or not is up to you. These are just sort of some preliminary questions. True or false? Get out your mental clicker. True or false? The vertical acceleration remains the same throughout. And that is true. What is the vertical acceleration throughout? Minus 9.8, right? Give yourself 1 mark if you got that right. True or false? The horizontal velocity remains the same throughout. In a non-air resistance situation. Horizontal velocity, Nate. So we don't know what it is, right? We don't know what it is, but it does remain the same throughout. Okay, so here's sample number 2. I would suggest you jot this down as a sample, as a model for your own work here. Sample number 2 is ball is hit at an angle of 30 degrees, leaves the bat with a velocity of 40 meters per second. Remember this here, when you're talking guns, is sometimes known as the muzzle velocity. It might also be known as the launch speed or something like that. Okay, so we're launching a ball at 30 degrees. It's leaving the bat with a velocity of 40 meters per second, and it's on level ground. So it's going to go like that, right? Parabola. So let's go ahead and find VV. And when I say VV, I really mean VIV, the vertical component of that initial velocity. Okay? So that's going to be VV right there, right, of that triangle. So it's opposite. So that's going to be sine. So it's simply going to be, it looks like I have it down here already done. Yay for me. V sine theta, 40 sine 30, 20 meters per second is the vertical component of the launch velocity. Same question. Now we're finding VH. Nate, come on. It's going to be V cos theta, right? Got it, Nate? Okay, so find VH, as Kurt pointed out. That's simply going to be V cos theta. Is it safe to say that to start all of these questions, you should find VV and VH right at the start? Pretty much, right? if you get lost somewhere along the way, at the very least, finding the horizontal and vertical components is certainly step one. And the time of rise. How long does it take to go up, right? Well, we're going to use VF equals VI plus AT, but which V do we use for VI? Do we use the 40, the 34.6, 20, or minus 9.8? Which one? Well, because it's time of rise, we're going to use the vertical, because it's the vertical that determines how high up it goes, right? You might remember that comment from last week. So we're going to use, oh, no, I forgot which one it was. We're going to use the 20. Okay? The vertical component is what we're going to use for VI. No, it's 20. That's what I'm saying. VF, good question. What is the VF? The VF is 0 because the time of rise, right? Does it ever stop? Well, at this point here, we're only interested in that point there, right? The time of rise. So how long does it take to get to there? So here, the initial vertical is 20, and here the vertical is 0. It's no longer rising at its peak, right? Now this 2.04 seconds is only to the peak, right? That's how long it takes to get to the top. So apply your rocket science skills and tell me how long does it take to hit the ground? 4.08, right? Or another 2.04 seconds. It's going to take just as long to go up as it's going to take to come down, provided there's no air resistance. And we're certainly making that assumption here just to make things a fair bit simpler. So VF equals VI plus AT, 20 plus minus 9.8 T, 2.04 seconds. Only to the peak. Okay, how high does it go? That distance there. Well, there's actually a couple ways to do it. You could use VF squared equals VI squared plus 2AD. Final velocity 0, initial velocity is that 20 again. Solve for D. Right? And I know you can all solve those kind of things. Is there another way to do it? Yeah, you also know the time it takes to rise based on that previous one. And so, whoops, let's make that readable. Either one of those is fine. Okay, so let's move on now. I think the next question is, the time of fall. Okay, I'm just going to prove to you that it's 2.04. Right? We know, it's up to you. Your notes, Nate. I'm not the notes police. I'm not going to arrest you for, I don't know, inadequate note taking. The drop is 20. We do know that if it goes up 20.4, we can guarantee it's 20.4 down as long as it's a flat surface. So if I were to take a displacement of minus 20.4, why is the initial velocity here 0? Because it's going down, right? It's reached its peak. It's reached its peak, so the VI is equal to 0. 1/2 AT squared minus 9.8 is our acceleration, and you get, no big surprise, 2.04 seconds, which of course is the same as T up. Pam has a question. No, I'm good with, yeah. This is just proof that it's true. Yeah. We're all big boys and girls. I'm sure you can just say, therefore, it's the same as the time down. Yeah. Yeah? They're a lot of fun, eh? Said no one ever. Okay, time of flight. Now, I am going to show you both ways because I'm leading into something tomorrow. So obviously, you could just say 2.04, 2.04, 4.08, right? I'm going to show you something that sort of proves that another way, and it leads us to something what I call sort of an elegant solution when it comes to the next problem. So let me just do this. I don't know, Nate. Let me finish this, okay? Okay, so I'm going to say, I'll make that a bit bigger. I'm going to say that the total displacement is 0. Why did I do that? Yeah, the vertical displacement is 0, right? It starts at some origin in the ground, it goes up in the air, and it comes back down, and the overall displacement is the same as before. It's 0, right? So if I plug 0 in for my displacement, my VI is plus 20t, plus 1/2 minus 9.8 t squared. And then you're going to get 4.9 t squared minus 20 equals 0. Can you factor that? Yeah, you can. You can take out a t, right? So it's either going to be t times 4.9 t minus 20 equals 0, which means that either t is equal to 0 or 4.9 t minus 20 is 0. The displacement is 0 when the t is 0. Well, of course, right? When no time has elapsed, it's just sitting there. It's at 0. When 4.9 t minus 20 is 0, so then you're going to have, oh, I should have put equals. That's mathematically bad. So then you'd have 4.9 t equals 20. T equals 20 over 4.9. 20 divided by about 5. What do you... 4.08. Right? So I'm just showing you that time is at 4.08. Now when we get to tomorrow, because it's not going to be a displacement of 0, we're going to have a c value. So we're going to have to do what? Use the quadratic formula. And guess what? And whether you write that down or not is up to you. I don't care. You know how to use a quadratic formula. You're going to get 4.08, right? Tomorrow, I'm going to show you problems where it's coming off a cliff, and again, that displacement is not going to be 0, which is going to give us that c value, which is going to lead into a necessary quadratic formula, right? Because here, time up is equal to time down, but if I launch it off a cliff, is the time up equal to the time down? It is not, right? So that's why I want to sort of give you this preview of this sort of stuff over here on the left. Okay? Everybody kind of understand what I'm doing? I'm sort of giving you a preview for tomorrow. I think this little bit here is just taking the 2.08. Yeah, it's just doing that. Right? For now, level ground, I'm happy with this. But I wanted to prove it to you mathematically. Pause there for a second, in case someone's jotting that down. Question, the one that most people are actually interested in, is the range. How far does the guy hit the ball? Right? Pretty far. Is the VH a constant 34.6? It is, because we are assuming, whoa, we are assuming no air resistance, right? So the VH remains 34.6 throughout the entire trip. How long is the trip? 4.08. So this is actually the easiest problem of the bunch to solve, because it's just that, right? V bar equals d over t. We can use this because it's a constant velocity. 34.6 is equal to d over 4.08. Multiply it out. The baseball, or whatever it is, travels 141 meters. It's a pretty good hit. 141 meters, that's like 1.5 football fields. It's a long ways. Sometimes you'll see baseball players, they'll hit baseballs, home runs that don't go out of the park, like they'll hit something, and they always calculate how far the ball will have gone. So they'd have to do some sort of calculation like this to figure out how far he actually hit the ball, even though it, hit the wall like 8 stories up the outfield wall kind of thing. Now, velocity to impact. before we go any further, will the final velocity be different from the original launch velocity? What was the original launch? 40? It will not be different, so Mitch is saying it will be the same. Okay, so let's work it through and see what happens. So the V, the velocity of impact, and I hesitate to put VI for impact, right? So we'll just call it V, is the vector sum of VH and VV. All right? The VH is what? 34.6. It doesn't change. The VV is the final velocity for an object that has fallen 4.08 seconds, because that's the total time. So I'm going to use VF equals VI plus AT. Notice here that my VI is 20, right? Because the initial vertical component is 20, plus minus 9.8 times 4 seconds gives you VF of minus 19.98, which is, for all intents and purposes, right? How come it's not exact? No, it's actually only by rounding. That 4.08 wasn't an exact number. It's actually rounded a bit, right? So the VF, if it was launched at a vertical component of plus 20, the VF is minus 20. Something's going on out there in Grandview. All good? Little problem with the smartboard? So, what does that mean then? I think you already know the answer, right? So to find the overall velocity and direction, we're going to set up our little triangle. Use Pythagoras. V squared is 34.6. That's the horizontal. The 19.98, it should be negative, but it doesn't matter. We're going to square it. And what do you know? You get 39.96, which is, for all intents and purposes, is 40 meters per second, right? I would do the reorientation, but it's not worth it. So yeah, Mitch is absolutely right. The launch speed of 40 is maintained at the end, is the same at the end. Again, this is only true when air resistance is negligible, because air resistance is going to slow that horizontal down, which is going to make that 34.6 less, which means that it's actually going to be less when it hit, right? Yeah, like when a guy catches a baseball, it doesn't hit him in the glove as fast as it leaves the bat, that's for sure. Air resistance is substantial. The answer is only the same because we're assuming there's no air resistance. It's a whole lot harder when there's air resistance. What about the angle? A little bit when we do the Hot Wheels one. Hey, you were going to bring me that car. Did you bring me that car? So tan theta, 19.98 over 34.6. Opposite here, opposite over adjacent. Coming up this week, yeah. You're going to get 30 degrees. It's exactly the same. It's symmetrical. Except it's 30 degrees below the horizontal, or if you prefer, kind of looks like one of the heads from Easter Island a little bit when I drew it like that. Note that the final velocity is exactly equal to the initial velocity. Pardon me? Yeah, if you're going to what's the main idea? Well, the main idea is that the final and the initial are the same, and really, the most important thing to be able to calculate is the range, right? That's what people want to know. How far does the ball go? I'll post it all to Schoology right away, Nate. So. Yeah. Well, I'm giving you all the background, right? Now you just have to use this knowledge that I've given you. Will I expect all of this on every question? No, of course not, right? I'm giving you the background knowledge. You guys do the problem and prove to me, sell me that you know what's going on. Yeah. No? Schoology doesn't like you, I heard. Every dislike, there's an equal and opposite dislike.
So we can say